Okay, so after downloading this project, let's add a file to it and name that file as traversals.c. So what we are doing, all traversals we are going to write in a separate file so that our project is well organized. So Rushank, how do I add a file to this? In file, what on this? Okay, then
no, right click on the project. And
okay, right click on the project. Right click,
add files.
add file. Add files recursively. No, this is not the option. This means we want to include files that are there on the disk. But what we are doing right now is we are adding one more file to the project. That either we do using this or we do using file menu, new. There's a file. So let's go to file and we want to add a C file. Say go, select C and let's browse. What is the name we want to give to the file? Traversals. Enter. And we should also include them in debug and release and say finish. With this we'll see a new file gets added to our project. So add this because today's code will write in this. So how many important traversals are there? 3. Which one? In order, pre-order, post-order. And in pre or post, tell when root will be printed. If it is pre-order, root is printed first. In order, root is middle. Post-order, root is last. So if we take an example of this, what is pre-order of it? 213. Pre-order is root, left, right. Post-order? Post-order is, yeah, first 1, then 3, then 2. Root in the end. This is post. And in order? 1, 2, 3. There is one more traversal which is popular, and that traversal is called level order. That means first print the nodes of first level, which means 2. Then come to second level, 1 and 3. If they had more levels, let's say here was 5 and 7, here it was 6 and 9. What will be the post order traversal of this? Sorry, level order. 2, 1, 3, 5. Okay, this is 7. 5, 7, 6, and then 9. So Lokesh, this is clear. What is level order traversal? We are going level by level. First root level, print that. Then left to right, print this level. Then left to right, print this level, and then this level. If this is the order in which we are printing a tree, we call it level order traversal. So we will start with level order. So let's come to bst.h, because all the function declarations we are including here in header file. So what should be the signature for level order traversal? Level order traversal is the function name we are giving. Ajay, what input parameter will it take? It will take root. Anything else? That we have to keep track of. So given a tree to us, we have to go level by level. So that is our logic, how we track level. We are not talking about printing one particular level. We are talking about print entire tree level by level. So this is good enough. What will it return? Return type? Void. Why?
What is the data?
Traversal is, what does traversal do? It just prints the tree. So do we need to return something? No. So void was correct. So we do void level order traversal. And given any tree, it should be able to print that in level order. void level of order BST node. So let's go to main now. Comment out the previous code. We add a unit test for level order so that we will be able to test our function once we have written it. Void level order unit tests. I'm copying first line from previous function, first two lines. So we are just creating a random tree and printing the ASCII, printing the tree. After that we will call our function level order traversal with root, which for now we have not written. And from main we will call level order unit test. This we are doing so that we don't use pen and paper to see whether our output is correct. So till now what we have done is, in bst.h we have added a declaration for level order traversal. In main we have made a call to unit test. In unit test we are creating a random tree, we are printing the tree and we are calling level order traversal. Now we should write the code for level order traversal. So let's copy our function signature from bst.h. Where will we implement it? Traversals.c. So we come to traversals.c, we paste that signature, and this is where we will start implementing it. Rishank, you are done with code in main? You have written the unit test function, you have made a call to that? Or you are typing? Okay, no problem. Type, then we'll start further. Tell them for locations I, you have done right. Will the code compile if I compile it now? No. Why? Yeah. In this file we are using BST node. It won't know what is BST node. So we do hash include bst.h. Done, Rishank, now?
Start.
Hmm?
I will.
No, we'll go together. So what is missing? In main.c, okay, first thing that we did was, we went to bst.h, we wrote this signature here. You are done with that? Perfect. Ajay, you are also done with this signature in bst.h? Not done? Okay, so add the signature. Have you added traversals.c to the project? Okay. Ajay, you have added traversal.c? Okay. Let me add the checklist. Traversals.c I have added. That is first thing we did. In bst.h, add signature for level order traversal. So this is what we did next. Third step, what we did? in main.c, add a function and the function signature was level order unit test. And fourth step we have done is, in that function we have made 3 calls. And fifth step, call level order unit tests from main. Are you done with these 5 steps? Okay. Then we did a 6th step, copy function declaration from bst.h to traversals.c, because that is where we will implement it. So coming to traversals.c, this is where we have copied that signature, we removed the semicolon and made the function body. And 7th step we did hash include bst.h in traversals.c. It's all there. Okay. So now today what we will do is, I'll tell you the logic how we are going to write this. You need to convert that into code. Okay. For now, let me run it and show you. If this is the tree, what will be the level order traversal?
41,
So it will be level by level. 41, 34, 67. 0, 36, 58, 69. They are at the same level. Then 24, 45, 62, 78. Then 5, 27, 42, 61, 64, 81. Then 91, then 95. That is what level order traversal is. Now how do we do level order traversal? For this we need a separate data structure which is queue. Okay. So if we are using queue, previously you remember we have created a library. First thing that we will do is we'll call create queue function. Using that we'll create a queue. So general, it was queue is equal to create queue. This is how we had written our queue code earlier. And then in the end we say destroy queue and we pass queue to that. So we need a queue here. Now we'll see why we need a queue. Let's say we start from root. Can we print root directly in level order traversal? Because that's the first thing to be printed, right? We print that. After that, we check if it has left child and right child. Its left child should go on top of queue, in front of queue. Or let's start like this. So let's create a queue. From the beginning itself, till now we have created a queue in the code that we have seen. First thing we can do is we can put our root in the queue, 41. Insertion happens in the end, queue did not have anything, we have inserted the first element. Now in a loop, we keep on going in the queue till the queue is empty. We want to dequeue from the queue. 41 we have enqueued. Now first thing we do is we dequeue. 41 gets dequeued. After dequeue we print it. So we are doing dequeue, then print, and then we are checking if it has left and right child. So first left child is 34, we enqueue that. Then right child is 67, we enqueue that. After that we go again on top of loop. In this loop what we are doing, every time we are dequeuing one item, if it has left and right child, we push them, we enqueue them. So now next DQ happens 34. 34 comes out. Its left child is 0. That we NQ in the end. Right child is we DQ in the end. And 34 gets printed. So till now 41 is printed. 34 is printed. Now we DQ 67. So after 67 is DQ'd, we print 67. Now 67 has 58 and 69. So 58 and 69 they get NQ'd. Then who gets DQ'd? 0. 0 has only right child, no left child. So its right child will be NQ'd, which will be 24. So this way if we keep on going, Q gives us a mechanism which is printing level by level. So now you can convert that into code. So initial setup I will tell you. We are doing Q star Q is equal to create Q. Because we have imported all the code here that is available. In the end we say destroy Q, Q, and we write an infinite while loop. Before entering the loop, we NQ. In Q we NQ root. So in loop you have to DQ, print, and then you have to NQ the children. How do I DQ it? DQ, it takes input parameter Q, from which Q we are DQing, that's it. And what will it return me? BST node star. Here I can write either BST node star TMP equals this. Either I can write this, or now I can also write LL element type, which will be void star. But it's better to keep it in a specific pointer so that we can access left and right of that. So now once we DQ it, what do we want to do with this item? After DQ, we want to print the data. How do I print this data? Printf %d, let's give a space, and then if we don't give space it will appear together, so that will be a problem. So temp of data we are printing, and temp of data we know temp is BST node, and in BST node our element type right now is integer. That's why we are printing using %d. If that was a character, we would have printed using %c. Now after we are done with this, what we do? We NQ left and right child. So can I say NQ Q comma temp of left, and then NQ Q comma temp of right. That we NQ. And after writing this, let's try to trace it. Now we have written this logic. Let's trace with our example. Okay, I'm making a call. For now I'm commenting it.
So we should check conditions also.
Yeah, we should.
None of it not equals to
Yeah, right now it's not complete. That's why I'm saying we'll trace and we'll figure out what is missing. First thing, okay, this will not compile because we are using Q here. Q is coming from which header file? Q.h. So we should do hash include of that. Q.h. And QDQ will automatically come from there. And then in this function we are using, what is this line? Printf. Printf comes from stdio.h. Then we are using NQ function, DQ function, destroy. All of them come from Q.h, so that's fine. So now compilation should be fine. At least it is compiling. Let's get the tree and try to trace it. This is actually a bigger tree. So I'm making changes to my code, but you don't need to make those changes. So I want to start with a smaller tree and see whether it will give us the right output or not. So this is the tree we are seeing, and our while loop logic is font visible to everyone? Okay. So let's try to see what it will do. First time we are creating a queue, which is, let's say this is the queue we have created. First line number 7. Then we enqueue queue and root. What are we enqueuing? A node containing 41. This is complete node that we have enqueued. After that we enter the while loop. After enqueuing this, first thing we do is in temp we dequeue. What will get dequeued? 41. That is there in the temp. And then we print temp of data. What will be printed?
41.
That means we dequeued this, it is no more on the queue. When we dequeue, it is removed, and 41 is printed on the output. After that we come to enqueue temp of left. Who is left of 41? 34. We enqueue that. Next line we enqueue temp of right. We enqueue 67. These are the two things we enqueued. Now again we go up in the while loop. Condition is true. We dequeue. What do we dequeue? 34. So temp gets 34 node. This is removed from here. Then we print the data of that. That means 34 will be printed, and there is a space, 41 space. Now enqueue temp of left. Who is left of 34? 0. We are enqueuing that. Who is right of 34? Null. We are enqueuing that also. That means we will be enqueuing null here, and it's okay to enqueue null. It's possible because it's a queue of pointers. Null also can be enqueued. But did we want null to be enqueued? No. So how do we avoid that from being enqueued? We can put an if condition. If temp of right is not null, only then enqueue. Same way, if temp of left is not null, only then enqueue. Now what will happen if we enqueue null? Every time we are dequeuing, next line we are accessing the data of that. Now if we dequeue a null, it will crash. So first thing we want to ensure is we don't want to enqueue nulls. So let's incorporate that change. If temp of left is not equal to null, then only enqueue it. Same way, if temp of right not equal to null, enqueue it.
Also check for temp not equal nulls.
Now since we are dequeuing, we are never enqueuing a null. Are we enqueuing a null now after these checks have been put? We are not. So in that case, we will never dequeue a null. So temp will never be null. Can we say that?
Initial.
Yeah, initially, that's a good point. Initially, we are not checking whether root is null. If root comes null, we are enqueuing here. But that also we want to avoid. So what should we do for that?
Root not equal.
If root is null, do we have anything to print? Simply return. So that also we avoid. That's a good catch. So now our code ensures we are never enqueuing a null pointer. First time we are enqueuing root, and root null check we have incorporated on top. Then we are enqueuing temp left, temp right. Both of them we are checking for nullability, and that's how we are going. Now one problem is there, the loop is infinite loop. When will this loop break?
If both left and right are null.
If both left and right are null, okay, let's see. In this case, when we are enqueuing 0, its left and right are null.
For both sides, left one and right one. Both if they are null, it will become right.
Okay, but queue will still have elements. Let's see. So first thing that goes in queue is 41, then 34 and 67. Yeah, when queue is empty is a better check. And another thing is, if queue is empty and we do a dequeue, what will happen? We have put assertion there, because we cannot do a dequeue in an empty queue. So can we put a while condition? While not is queue empty and queue. Till the time queue is not empty, we can do what we are doing. And this also protects our DQ call, that we are checking for empty queue in the beginning. Or since we started with an infinite loop, it was okay to include this condition here. If is queue empty, break. Both of these things are fine. Either we include in the while loop that condition, or we include inside the loop. Because we know if queue is empty, we have to break. There is nothing else to be covered. And before executing it, we'll print one more thing. In the beginning of this, we'll print a line, level order traversal, so that the complete traversal, when it is printed on output, we can know this is coming from level order traversal /n level order traversal. And we have included a check also. Okay, I missed a semicolon here. In this printf, I missed that semicolon. Now it will compile. Okay, I have commented the call in main. So traversals. Now if we run it, you will see for this tree it is saying level order traversal is 41, 34, 67, 0, 69. I changed my main logic. I made it 5 nodes. Let me make it 20 nodes. Now when we run it, because we are going to cover other traversals also, that's why I have put this line in front. Level order traversal column, all of them we are printing in one line. Lokesh, working? Okay. Just see. So we again go back to bst.h. You can copy the last line, level order traversal, paste it, because signature is going to be the same for all the traversals, and level we change to pre. So just add one function signature to bst.h and call it pre-order traversal. And then we copy that signature to traversals.c, because we want to implement it there. Now what is the pre-order for this tree? We'll print 41. Then in pre-order, root is printed first, then left, then right. And when we say left, it is left subtree. So after 41 will be printed. We have to print this entire left subtree. Then we come to 34. But from 41, when we move our pointer to 34, we miss track of the right subtree. Ultimately, we want to go back there also, right? So when we print 41, can we use Q here? From 41, after printing 41, we are moving root is equal to root left. Then go to 34, print it, root is equal to root left. 0, print it. 41, 34, 0, printed. Now what if we use Q, from 41 when we are going to 34, we are afraid that we will be losing the right pointer. So that let's say we NQ it. So 67 is NQ'd before root is changing from root to left. Let's take a Q. We come to 41, we print 41. And after printing we NQ 67. Then we change 41. If 41 has a left child, we move down. So we come to 34. After coming to 34, again we do the same thing. We print it. We NQ the right child. Who is the right child of 34? 36. And again we go left of that. We come to 0. After we come to 0, first thing we do is we print. Then we check if it has a right child, we NQ it. Who is the right child of 0? 24. We NQ that. Again we move this to left of it. Now left of this is null. If left subtree is done, then next element we pick from the Q. What is the next element in Q? 67. Can we go directly to 67? No, because we are not yet done with the left subtree. So this makes Q as inappropriate data structure to be used with pre-order. So let's try with stack, whether stack gives us the right thing. So now let's assume this is the stack that we have. First, when we go to root, we print it directly. 41 is printed, and because we don't want to lose right pointer of 41, for now let's NQ 40. Let's push 41 itself. So 41 we are pushing. Then we go to the left of that, 34. 34 we print and we push 34 also. We go to 0. 0 we push and we print 0 also. After 0 is done, 0 does not have left child. That means left part is done. Now, what is the next element we pick? Once the left of this is null, we pop from the stack. And after popping from the stack, we know the element that we have pushed on the stack that is already printed. Then we have to go to the right of that. Who is right of 0? Right of 0 is 24. Now we go to 24. And with 24 we do the same thing. 0 is popped. 24 we push. We print as well as push. After 24 is pushed, again we go to the left of it. Left of it is 5. 5 also we push and we print also. So here with every node what we are doing is, first we come to a node, we print it. If it has a left child, we move to the left. And before moving to the left, we are pushing that onto the stack. So this pre-order traversal will have a stack in it. Stack star s is equal to create stack, and in the end we'll do destroy stack of s. Here again we'll use the while loop, infinite while loop. First thing we want to cover is left. Print and go left. Then we want to pop. Once the complete left is over, we talked about if no left child is there, then we want to pop, and after popping move to the right of popped element. So basically our next element to go to is, if pop we are doing in, let's say, temp, all we have to do is we have to say temp is equal to temp of right, and we can again go to the top of the loop and start the same procedure. So now try writing this code completely. Again include the root null check, the condition where the loop will break. It's similar to what we have done now, just that rather than using queue we are using stack. And another thing is, when we make recursive calls, stack is automatically there because function call stack is built. So rather than using the system stack, we are creating our own stack. Can we say we are doing this? We are printing the data of current node, we are pushing the current node, and then we are moving to the left. And this we have to keep on doing till we get to the extreme left node. While temp not null, so you start from 41, print 41, push 41 and come to 34. Print 34, push 34, come to 0. Print 0, push 0, come to null. Once we reach null, this loop is done. And we have reached the extreme left. So we are continuously coming to the left. Now all we have to do is we have to pop the last element, and the element that we are popping, we know that has already been printed. We have to move to the right of that. So that is what we had already written. Next we will pop, once we are here, we will be popping 0. 0 is on top of the stack. After that we are saying temp is equal to temp right, which is 24. So termination of this loop has to be ensured. So before popping, if is stack empty s, then we simply say break. There is nothing to do. Now, what if root is null in the beginning? Will this be already handled, or we need to add that lines? Let's trace with root null. We have created a stack, we have assigned that to temp. We come into this loop.
No need to.
No need to?
Not equal to null. Because we kept a condition.
Yeah, we kept a condition here. This while loop, it will not enter. If it does not enter, there is nothing being pushed. We come here, is stack empty will be true, and we will break. So ideally, if we don't put that condition, even then it is fine. But in that case also, we are creating a stack and we are destroying a stack. Create stack makes a call to malloc, and destroy stack freeze it. If we want to avoid that nothing should happen, then we can put the condition on top. Otherwise, code wise it is perfect. So let's include that condition. If root is null, we simply return. Otherwise, we print a message: pre-order traversal colon . And another thing is, now we are using stack, so we should do hash include of stack.h, because earlier we did q.h, now stack also. So after we have written our code, in main we can go and add unit test. So rather than creating a separate function, I have added one more line into level order to unit test. In the end, just one more call to pre-order. Later on we will change name of this function to Traversals unit test. because all of the traversals we can check using this. So let me name now itself Traversals unit tests. So level order I'm renaming so that all the traversals we can call using this function. And then if we run, each line will give us one traversal. Roshank, done? Working? You have added the unit test also?
Yes.
Perfect. Ajay? First we'll start with bst.h. There we go. Copy paste pre-order function signature and call it in order. Then we come to traversals. We copy complete function pre-order traversal, paste it and call it in order. And printf we move to after pop. So after popping we print the data and rest all remains the same. So only changes we have done is printf we have moved from while loop to after pop. In pre-order we are pushing, we are printing and pushing. So after popping we were never printing it because we know that is printed. In order we first print it and then we move to the right of it. And after that if we run our code, we'll see it starts with leftmost child is 0, then 5, 24, 27, then 34, 36, 41 and right subtree.